Hello and welcome to Arithmetica and the first episode of Arithmetica's introduction to mathematical sets. The study of set theory is a rather important area of mathematics. Indeed, in the sense that mathematics is frequently argued to be the language of physics, set theory is often regarded as the language of mathematics. As we progress through the series, I will provide further depth to previously disclosed topics as well as the gradual introduction of new concepts and principles of mathematics in the study of set theory. And so, as this is the first video in the program, I shall be covering the very basics of set theory, starting with a brief history of its initial development, followed by some simple examples and properties of what mathematicians call the real numbers. And so, here is Arithmetica's introduction video of sets. Set theory is one of the most fundamental concepts in mathematics. It is perhaps therefore surprising that it was not formally introduced until the 19th century by the German mathematician Georg Cantor, following the work of Bernard Bolzano, a Bohemian mathematician, philosopher and theologian, of whom was perhaps most notable in mathematics for his highly rigorous and analytical approach, as well as for his somewhat controversial support in the notion of infinite sets. Cantor also had the good fortune in 1872 to befriend the German mathematician Richard Dedekind, of whom is known for his work in abstract algebra and number theory, inclusive of his work concerning the definition of the set of real numbers, together with his studying of the irrational numbers, i.e. those real numbers that are not rational, and thus cannot be written in the form of p over q, such that p and q are integers, i.e. whole numbers, and with q non-zero. It is indicated that Richard Dedekind's abstract logical approach to mathematics was a contributing influence in Cantor's work concerning his formalizing of set theory, as well as ample historical evidence demonstrating Dedekind's support regarding Cantor's work in establishing a more formal setting of set theory and the infinite. A set can be described as a well-defined collection of mathematical objects, called the elements of the set. In naive set theory, any collection of mathematical objects can form a set from assigning a defining property to it. More formally, this is known as naive comprehension. In this video, we shall be focused on naive set theory. However, it should be understood that owing to certain logical paradoxes that arose from the system, new theories were formulated in the attempt to eliminate such inconsistencies, generally by introducing a restriction to what we can define as a set. This includes the Zermelo-Fraenkel axiomatic set theory ZF, with its limited comprehension axiom, so designed to do just that. For example, we could take the defining property to be the first 5 positive even whole numbers. In mathematics, we often denote a set by a capital letter, as well as the use of curly brackets as part of our notational language to express a particular set. And so for our set with the property of the first 5 positive even whole numbers, we could write: this is a finite set, owing to the simple truth that only finitely many elements are included in it, in this case only 5. But for an infinite set, say all the even whole numbers, we often include an ellipsis, i.e. 3 dots, indicating that a particular pattern of membership continues. Thus the set of all even whole numbers could be written by. Alternatively, since the set of all the whole numbers, otherwise called integers, is normally denoted by the double-struck capital Z we could write, where sometimes we use a superscripted plus sign, so to emphasize that for this set, the whole numbers, i.e. integers, are positive, such that, and so, we then interpret the above description together with the set membership symbol of the set B as follows: 2 times n, such that n belongs to the set of positive integers. The set of natural numbers, often described as the counting numbers, is denoted by the double-stroke capital N. In number theory, it is normally defined as the set of positive whole numbers, that is, 1, 2, 3, 4, and so on. However, it should be understood that the word integer is usually favoured in higher mathematics than the term whole number. So in this case, we can write to describe the set of natural numbers as equivalent to the set of positive integers. We could then write the previously defined set B by. However, in mathematical logic, we include the element 0 in the set of natural numbers, such that it is defined as the set of non-negative integers, in which case the set of natural numbers is not equal to the set of positive integers. So we have. The context will normally make it clear which definition for the natural numbers is being used. As for the remainder of the video, it should be understood that I shall be using the definition of natural numbers as stated in number theory. We can also use other mathematical symbols to describe a set. For example, we could have used the less than symbol, or the greater than symbol, to describe the previously defined sets A and B respectively by Of course, in these examples, I have exploited our understanding of whole numbers and our familiarity with the denary or decimal system. That is, the number system that we use is what is called a base 10 positional or placeholder number system. A positional number system is very efficient for making calculations, and unlike the various non-positional number systems of the past, this also has the advantage of reducing the number of symbols used to denote any given number. This is because these are systems which have numerals up to but not exceeding the base used in the system, where the different positions of the numerals correspond to multiples of integer powers of the base of the system. Thus, for our positional denary system, we only need numerals up to and including a value of 9, and every number expressible in this system can be broken down into a summation of multiples of these integer numerals of powers of 10, starting with the units, and then tens, hundreds, thousands, tens of thousands, and so on. Most of the modern world uses the denary system to write their numbers, together with what we often refer to as Arabic numerals, owing to their origin. These are the numerals 1, 2, 3, 4, 5, 6, 7, 8 and 9, with 0 to represent an empty placeholder. But thanks to the advancements in Indian mathematics during the 7th century by the Indian mathematician and astronomer Brahmagupta, and prior its adoption into Islamic mathematics during the 9th century by the Islamic mathematician Muhammad ibn Musa al-Khwārizmī, 0 for the first time in known recorded history was being used as a number, together with arithmetical rules first proposed by Brahmagupta as to how one should use it in calculations. Before then, 0 was only ever used to simply denote an empty placeholder, and not every positional number system even had a symbol for 0. As an example, consider the number. The clue is really in how you would read this number, that is 306,407. We emphasize the recording of this number in the following table. The table shows the placeholders needed to represent this number in written form, as well as the placeholder's denary representation and as a power of 10. The corresponding integer multiple for each placeholder, as shown in the bottom row, is thus the numerals we write down to record this number. Thus in this instance we have 306,407 is equal to 3 times 10 to the power 5 plus 0 times 10 to the power 4 plus 6 times 10 to the power 3 plus 4 times 10 to the power 2 plus 0 times 10 to the power 1 plus 7 times 10 to the power 0, which of course is simply equal to the sum 300,000 plus 0 plus 6,000 plus 400 plus 0 plus 7. In general, we can express any integer in the denary system thusly. Let n be an arbitrary m-digit positive integer, then there exists integer numerals from 0 to 9 inclusive such that we may write n is equal to the sum from k equals 0 to m of 10 to the power k times a sub k, which gives us this expression here, where 10 to the power k plus 1 is equal to 10 to the k times 10, and 10 to the 0 is equal to 1. Where we have used the rule of indices, 10 to the x times 10 to the y is equal to 10 to the x plus y for any real number x and y, and a sub k for k equals 0, 1, 2 all the way up to m are the corresponding denary numerals. Negative numbers, i.e. those that are less than 0, are written similarly, that is with a negative symbol in front. Thus the denary system that we commonly use is part additive and part multiplicative. Now that we have some understanding of what is generally considered a set in mathematics, let us turn our attention to that of the set of so-called real numbers. This set is normally denoted by the double-struck capital R, that is by... Of course, in order to define the set of real numbers, we first need to have a precise definition of what a real number is, and then from that definition to establish the set of all such numbers that are real. There are a number of definitions, all of which can be shown to be logically equivalent to each other. However, in the light of the introduction, it would seem somewhat remiss not to formally disclose Richard Dedekind's definition of the set of real numbers. Before we proceed, I should give a formal definition of the set of rational numbers. With the set of integers defined previously as all the positive whole numbers 0 and that of all the negative whole numbers, i.e. the set, we define the set of rational numbers thusly. The set of rational numbers denoted by the double-struck capital Q are the numbers defined by P over Q such that P and Q belong in the set of integers but with Q not equal to 0, or equivalently P over Q such that P and Q belong in the set of integers but with Q strictly greater than 0, which of course is identical to insisting that Q belongs in the set of natural numbers. Thus, the set of rational numbers is simply the set of all fractions of integers, positive, negative, and 0. Examples of rational numbers include any integer, i.e. 1, 0, minus 4 or minus 123, as well as other fractions of integers, such as 1 over 2, 3 over 2, minus 32 over 9, etc. Now, for those rational numbers that are integers, we can use our positional denary system to write them down, as previously defined. But for those non-integer rational numbers, rather than write them in the form of p over q, where p and q are integers, we can use decimal notation to express them. In fact, all real numbers can be expressed in this way. Any real number x has a decimal representation written thusly. X is equal to plus or minus the sum of n plus the sum from k equals 1 to infinity of 10 to the power of minus k times a sub k, which gives its decimal form of plus or minus n point a sub 1, a sub 2, a sub 3, and so forth, where n is any non-negative integer and a sub k for positive integer k are the decimal numerals from 0 to 9 inclusive, together with the decimal point denoting the boundary between those numerals corresponding to integer multiples of powers of 10 with magnitudes greater than or equal to 1 and those that are strictly between 0 and 1. That is, it marks the decimal separation from the integer part of a number and its fractional part. Thus, in general, and to provide an alternative but equivalent expression, we may write x is equal to plus or minus the sum from where k ranges from minus infinity to positive infinity of 10 to the power k times a sub k. Noting again that we are using here subscript notation for the decimal numerals a sub k, but for this expression, k spans over all integers and thereby given its decimal form as shown. As an example, we have the positive irrational number 3 over 2, which we can write as 1 plus 1 over 2, and is equal to 10 to the power 0 times 1 plus 10 to the power minus 1 times 5, and gives its decimal form of 1.5. Or the negative irrational number minus 103 over 8, which we can write as the negative of 12 plus 7 over 8, and is equal to the negative of 10 to the power 1 times 1 plus 10 to the power 0 times 2 plus 10 to the power minus 1 times 8 plus 10 to the power minus 2 times 7 plus 10 to the power minus 3 times 5, and is equal to its decimal form of minus 12.875 precisely. From the definition of rational numbers, it is clear that in taking q equals 1, we simply obtain the set of integers. This tells us that all integers are rational numbers. Indeed, this observation would seem to be a good opportunity to present the concept of a subset. A subset of a set X is any collection of elements that are in the set X. Thus, as all integers are rational numbers, it follows that the set of integers is a subset of the set of rational numbers. Moreover, we observe that not all rational numbers are integers, since a rational number, p over q, is an integer if and only if q divides p. Clearly, 3 over 2 is a rational number, but as 2 does not divide 3, it is not an integer. We say that the set of integers is a proper subset of the set of rational numbers. This leads to the following definition. Let X be a set and Y be any collection of elements in X. Then Y is a subset of X, and we may write read as y is a subset of x. And if y is a subset of x, but not all elements of x are included in y, then y is said to be a proper subset of x. This is often written as, and is read as, y is a proper subset of x. Moreover, by the definition of a subset, it is trivially true that every set is a subset of itself, although obviously not a proper subset. We also define the set of irrational numbers as those real numbers that are not rational. That is, the set defined by x belongs in the set of real numbers, such that x does not belong in the set of rational numbers. That is, those numbers that cannot be expressed as fractions of integers. Popular examples of irrational numbers are the square root of 2, the base of natural logarithms, normally denoted by the lowercase letter e, which is equal to 2.718 correct to 3 decimal places, as well as the constant of proportionality of any circle's circumference with that of its diameter, normally denoted by the Greek lowercase letter pi, which is equal to 3.142 correct to 3 decimal places. Indeed, it can be shown that a number x is rational if and only if x has recurring decimal numbers in its decimal representation. This includes those numbers that have finite decimal terms, such as 1 over 2, which has decimal representation of 0.5, which we could write with recurring decimalisation 0.50 recurring, or by 0.49 recurring, that is, with infinitely many recurring zeros or nines respectively, where it can be shown that 0.09 recurring is equal to 0.1, although sometimes we write the recurring decimal with a line above it, and so the previous example could be written as, and so 0.49 recurring is equal to 0.4 plus 0.09 recurring, which is equal to 0.4 plus 0.1, which is equal to 0.5, which we can write as a fraction of 5 over 10, which of course can be simplified to 1 over 2 as required. Similarly, we have 0.9 recurring equal to 1. This seems rather counterintuitive, as one might expect that 0.9 recurring is smaller than 1, such that it is infinitesimally close to but less than 1. One method of proof is by showing that 0.9 recurring is expressible as a convergent geometric series with a sum total of 1. However, a simpler argument, which does not require prior knowledge of geometric series, is as follows. Let x equals 0.9 recurring, so that 10x, i.e. 10 times x, is equal to 9.9 recurring. That is, 10x is equal to 9 plus 0.9 recurring, which is equal to 9 plus x, as x is equal to 0.9 recurring. So 9x is equal to 9. Thus, by dividing both sides by 9, we obtain x equals 1. Hence, 0.9 recurring is equal to 1 by substitution. Thus, we have given a simple logical argument in showing that 0.9 recurring is equal to 1, thereby providing the required result. Indeed, from this, it immediately follows that 0.09 recurring is equal to 0.1, as previously claimed. Of course, we can equivalently define the set of irrational numbers by stating that a number x is irrational if and only if x has non-recurring infinite decimal numbers in its decimal representation. This is the reason why we can never state the exact decimal representation of irrational numbers like pi. Rational numbers, however, can always be written exactly, whether it is in their decimal form, admittedly with the possibility of recurring decimals, or as fractions of integers. From the given definitions of the set of rational numbers and the set of irrational numbers, we can provide an informal description of the set of real numbers as those that make up all of the rational and irrational numbers. Therefore, from what we know so far, it follows that the set of rational and irrational numbers are both proper subsets of the set of real numbers. Moreover, by the transitive property of subsets, proper or otherwise, since the set of integers is a subset of the set of rational numbers, we deduce that the set of integers is not only a subset, but is also a proper subset of the set of real numbers. In fact, the set of real numbers should have some familiar properties. For example, it is meaningful to speak of their order, such that we can communicate whether a given real number precedes another, expressible in terms of inequalities. That is, we can communicate the fact that 3 precedes 5 by stating that 3 is less than 5. Mathematically, we can write this inequality by using the less than symbol, which was introduced earlier in this video, so that for this example, we have 3 is less than 5. Similarly, we can provide the logically equivalent statement that 5 is greater than 3, so that in using the greater than symbol, we have 5 is greater than 3. Indeed, an important property of the real numbers is that if x and y are any two real numbers, then exactly one of the following is true. X is less than y, or x is equal to y, or x is greater than y. This is often called the trichotomy rule and can be written symbolically by. We can describe this property of real numbers as an order property. Other important order properties of real numbers is as follows. The transitivity property. Let x, y and z belong in the set of real numbers. Then if x is less than y and y is less than z, then x is less than z. And there is the Archimedean property. Let x belong in the set of real numbers. Then there exists a positive integer n such that n is greater than x. This property is sometimes expressed in a different form and is named after the Greek mathematician Archimedes of Syracuse. And finally, the density property. Let x and y belong in the set of real numbers, where x is less than y. Then there exists a rational number p and an irrational number q, such that x is less than p, which in turn is less than y, and x is less than q, which is in turn less than y. That is, between any two real numbers, there exists rational and irrational numbers. Indeed, one consequence of the density property is that there are infinitely many rational and irrational numbers between any two distinct real numbers. As a visual aid, the set of real numbers is often presented in the form of a number line, as shown here. We can normally visualize the set of real numbers by starting from 0 and extending either side of it to include the positive numbers in one direction and all the negative numbers in the other direction. The labeling of our number line also includes the negative rational number -1/3, as well as two positive irrational numbers, the square root of 2, which we can see is strictly between 1 and 2, and pi, which we provided a definition earlier in this video, and is evidently a little greater than 3. Naturally, we can provide greater accuracy for the decimal representation of irrational numbers using various numerical methods, and will feature as a topic in a later video. Another and perhaps more difficult concept to comprehend is the notion of infinity. The number line shows that the real numbers tend to plus or minus infinity. That is, the real numbers become arbitrarily large, whether positive or negative, and we say that the set of real numbers is unbounded. During the course of this video, the general concept of a mathematical set has been introduced, together with some simple examples. Such examples included sets of natural numbers, as well as formal definitions of the integers and that of the irrational and irrational numbers, and on how we use the decimal system to express them. This led to our informal description of the set of real numbers, where I concluded with some important properties and a useful visual aid representing this set, which depicts, among other things, the unboundedness of the set of real numbers. In the next episode on Arithmetica's introduction in set theory, I will provide further thought on some of the properties of the real numbers, including numbers that we probably take for granted, as well as a precise definition of what an unbounded set of real numbers is. The video will then conclude with the formal definition of the set of real numbers by Richard Dedekind, as promised earlier in this video. And so, until next time, it's goodbye from Arithmetica.